In this video, we're going to talk about different types of bonding between atoms. So we've seen a little bit of this already. We saw ionic. Ionic bonding is when you have charged particles which are attracted to one another. So if I have a large plus object and a large minus object, as they drift by each other, they're going to be drawn towards one another, and they will pull up side by side and just be next to each other. This is very much like magnets. If you have two magnets and you kind of bring them near each other, opposite charges on the magnets attract, they pull together, and they just stick to one another. And that is all ionic bonding really does. I have a charge, opposite charge sticks to it. Now, you can pile up many of these in alternating patterns to make larger and larger crystals. If you think of a small grain of salt, it's a very tiny arrangement of a lot of ions. But if you've ever seen one of those really large plates of salt, you can buy them sometimes at various cooking stores. They're good for putting fish on. It draws a lot of the moisture out of the meat. But those are very, very large salt crystals. And they're just one continuous pile of charges alternating back and forth like this. And so ionics just pile up on each other. You get more and more and more of them piling together. Now, ionic has a few properties as a result. They tend to be very high boiling and high melting. So high boiling point / melting point. It takes a lot of energy to pull a huge mass of magnets apart. It's not an easy thing to do. And so you have to be really hot before these will liquefy, and especially before they will turn to gas. They also tend to be quite brittle. Now, they can be remarkably tough. Some ceramics, ionic compounds, are some of the hardest materials there are. But what tends to happen is they resist change until they fail all at once and shatter. If you think about what's going on for that, well, if we look at our ions over here, I've got some negatives and positives near each other. If this shifts down just a little bit, well, now I have positives and positives near each other. That's not good. And I have negatives and negatives near each other. Those repel. If you've ever held two of the same side of a magnet near each other, they push apart. What happens if you have a salt crystal or glass or other materials like that? It's very tough unless you put enough force to push part of it down. If you can get the ions to slide a layer down, they then shove themselves apart. So why, if you hit glass in one spot, does it spread throughout in these huge cracks throughout it? Because if you hit it hard enough to crack it in one spot, you put the ions out of alignment. And so they tend to shatter, which is what we mean by brittle in this case. Now, it can take an enormous amount of energy to achieve that, or it can be pretty darn simple. Just depends on what the ionic compound is. Well, after ionic, a very common one we see is metallic. Metallic bonds are a little bit different. So instead of the ion just pulling up next to another ion of opposite charge, the way metallic works is it's actually the atoms. So I have the nucleus. Proton, neutrons, protons, neutrons, which I'm going to just draw generically as a positive. Right? And around them were electrons. Well, that's still true. There's still electrons out here. What will happen with metals, though, is those orbitals that the elements are in, they are very far from the nucleus. So when we talked about the s, the p, and the d orbitals, well, d orbitals are really far away most of the time. And so what happens is I have a neighboring nucleus, and it has its own orbital. And they actually overlap into each other. This means that the electron from one can at times actually be closer to the other nucleus than it is to its own. As a result, those nuclei, well, the protons in them are attracted to the electrons, and so they both pull towards that electron. What happens is you get a vast array of overlapping orbitals. And most of our metals are early in the periodic table, and those are the largest atom sizes. That means they have the largest orbitals. And so the alkali metals, your sodium, your potassium, the alkali earth metals, your calcium, magnesium, the transition metals in the center of the periodic table. The reason they're all metals is that they're big. Their orbitals reach really far out and overlap heavily with their neighbor. Result is you've got these electrons being shared all over, heavily interacting with each other. Well, because of this, they're not really strongly bound to any one atom, which means if you have an electron come in from outside, it can push the next one over, and push the next one over, and push the next one over, and push one out. Effectively, if you push an electron in one side, you get an electron out the other side. This is conductivity. This is why metal carries electricity. They can move electrons quite easily. And so metallic systems tend to have a few properties. They tend to be good conductors. They move electrons quite freely. Additionally, metallic systems tend to be malleable or very ductile. What this means is they can be shaped without breaking. If you take an ionic compound, you hit it with a hammer, it shatters. But if you take a chunk of steel, especially if it's a little hot, and you hit it with a hammer, it deforms. It reshapes itself. What happens is, unlike ions, where you had opposite charges trying to align, let's see that back up here, with metals, if you just hit part of these with a hammer and they get bumped down, well, as far as they're concerned, they're still sharing electrons with their neighbors. They're just as held together as they were before. And so you can keep hammering this and shifting bits over a little bit to reshape your metal over and over and over until you've shaped it into whatever shape you want, because as long as they're still next to their neighbor, they're still sharing electrons and holding together. And so you can bend and deform metal into all sorts of shapes. This is how blacksmiths were able to turn iron and bronze and such metals into the various shapes. These days we tend to use stamps. If you ever look up aluminum can manufacture, it's actually pretty neat. They just take a sheet of aluminum and punch it straight down through this material that has very thin layers of concentric rings that get smaller and smaller. So you got one ring this big, one ring a little smaller, one a little smaller, one a little smaller, and an aluminum sheet, as it gets punched down, just fills that bottom part, and you end up with your aluminum can. So you can find YouTube videos for making aluminum cans. It represents nicely, though, the idea of metals. Metallic bonds, they're very conductive, and they're very ductile. They can be manipulated and bent and twisted quite easily. Well, we've talked about ionic in its own videos. We won't go too deep into metallic. We will talk about a third type quite a lot, which is covalent. Covalent bonds are what we think of when we think of organic molecules. Covalent happens with elements in the upper right of the periodic table. So think about the periodic table. This section over here. This is the upper right. This is the non-metals. So these are elements like boron, carbon, nitrogen, oxygen, fluorine, and then down their columns. Sulfur, chlorine, bromine, iodine, phosphorus. There's a zigzag in the periodic table. This isn't all of them, but that zigzag in the upper right of the periodic table kind of blocks off the non-metals. Hydrogen is also included in this, even though it technically shows up over here. Hydrogen is just an exception to a lot of rules. It shows up in the non-metals for bonding. So what is a covalent bond? Well, the non-metals, as you got further to the right on the periodic table, you got smaller. As a result, you didn't have the reach that the metals have to share electrons kind of in all directions. However, you are very difficult to remove electrons from. all the elements in the upper right tended to be anions that want electrons. As a result, you can't really make them ionic in terms of having cations, and you can't share your electrons in all directions, but if they run into each other, they share one-on-one. And so covalent is a atom-to-atom sharing. What this means is if I have a hydrogen and another hydrogen, they'd be a proton with electrons around it, another proton with electrons around it. As they get closer to each other, they will overlap their orbitals, and they will share. In some ways, this kind of looks like metallic, but the problem is it is very, very short distance, and they're not able to get more elements in around them. They can't do it in every direction the way metals can. So when this happens, those two electrons are shared just between those two atoms. In fact, if you have a larger molecule like a CH4, you have a carbon and it is sharing. Use a line to show a sharing of electrons. There's really two electrons there, two electrons there, two electrons there. It shares a lot of electrons, but it doesn't do it in every direction. The electrons shared to this lower hydrogen do not get shared with the other three hydrogens. It is specifically shared between those two atoms. Carbon actually has many electrons though, so it can share some to the other hydrogens. But once they are shared between one particular hydrogen and one particular carbon, those two electrons stay there. So this is very different than metallic in this way. They're not omnidirectional. They are very specific. Well, the result of this is that covalent bonding has some very interesting properties. Mostly that it can have an enormously wide varying sets of properties. Depending on what your molecule is, it can be very brittle, it can be electrically conductive, it can prevent electricity from being conducted, it can be a gas, it can be a solid, it can be a liquid at room temp. There's a lot of possibilities with covalent. This is why they're what make up life. Life needs a lot of variety to do all the different things it does, and covalent molecules enable variety very easily. So in conclusion for properties, ionic bonding is brittle and based on opposite charges. Metallic is sharing in all directions and tends to have properties like being malleable and conductive. And covalent is sharing between two atoms, and their properties are varied. The most important properties we'll discuss in future videos, but tend to stem from the fact that they can take very complex designs where ionic and metallic are not able to take complex designs. They tend to just pile on top of each other. But covalents can have very specific, almost blueprint style angles and distances and looped connections. They make very specific constructions.